In this video, we are going to look at the 4 quantum numbers that can be used to describe an electron, and the 3 quantum numbers, the first 3 tell us where an electron is within an atom, and the 4th quantum number, the spin, tells us whether the electron is spinning up or down. Think of it like that. So the principal quantum number n, that we have seen on the Bohr atom when we calculate the energy when an electron relaxes to a lower energy state or a higher energy state. So this n is always integer values, 1, 2, and 3, and so on. And those are that describes the shell. So n is circles around the nucleus. We'll look at another slide in just a minute with that. The second quantum number, we may have not seen that in an introductory course, but the angular momentum quantum number, sometimes referred to as azimuthal, it's an older reference, describes the shape of the orbital. So L depends on n. So n is the shell, the L value is the subshell, and the values for L begin with 0 and go up through n minus 1. So we'll see some examples of that in a few minutes. The subshell, we may have remembered the letters S, P, D, and F. Those are different shaped orbitals, so we'll correlate those together. I'm just going to go through these really quick, and then we'll look at another sheet. The magnetic quantum number actually describes a specific orbital, and so we have just drawn lines or boxes for those. And then the electron spin, plus 1/2, we could just arbitrarily assign that to when we have an electron with the arrow facing upward, or minus 1/2 for the arrow downward. And these quantum numbers came out of Schrodinger's wave equation, and I'm just going to show us that. This is advanced for a general chemistry class, but we see the crazy math that predicted the crazy world of the electron. But this is a differential equation here. This is the Schrodinger wave equation. So if you take math up through Calc 3, then you can take differential equations, and entire equations have solutions. So this says the complete hydrogen-like atomic wave functions. And if we look here, we'll see n equals 1, L equals 0, and m, they didn't put the little l there, m equals 0. And so the wave functions are represented by this Greek symbol psi. So the 1s orbital, this equation is a solution to that differential equation. Then we can see when n equals 2, we have L equals 0 and m equals 0. So we'll go through these rules in just a few minutes. But I like to show this to my students because the strange business of quantum mechanics, it's hard to imagine physically an electron being able to be in 2 places at once, for example. And this theory actually came from pure mathematics first. And so the math predicted the strange quantum mechanical theory. If we go down, we might remember from an earlier class a 2s orbital, and then there are 3 2p orbitals, and so on. So when n equals 3, we've got a 3s, 3 of the p orbitals, and then that's where we add 5 d orbitals there. And we are just going to quickly look at the properties of a wave. but we see sines and cosines in here, so if you've had trigonometry, you know that a sine wave looks like that, starting at the origin, and a cosine wave is just shifted over 90 degrees. So anything that repeats itself can be described with sines or cosines. But I mainly show this so when students say they don't understand, I come back and say the math is where we got all of this theory. Okay, so that's not going to, if you read in your text about the Schrodinger wave equations, you might see psi, that symbol. And again, this is a little bit too advanced for a general chemistry course, but the quantum numbers that we're going to look at come from this math. And this is just the math of what waves can do. So if we consider, if we have a string fixed in position, maybe this could be a guitar string, and if we pluck the string so that it vibrates, if we could get the simplest situation happening would be the string just oscillates up and down. And if I knew music terms, I would probably know the musical definition of that. So we could get the string just oscillating up and down or vibrating up and down. And this really is where the S orbital shape comes in. Okay, so anything that can wave, so to speak, that would be the simplest case. If we had the same string, and one thing it could also do, if we pluck the string, it could pass through once and vibrate back and forth like this. And you may recall a p orbital has a shape similar to that. So all of this crazy, it seems crazy, business of the electron comes from the mathematics of waves. So Schrodinger's wave equations are generally easier to decipher than Heisenberg came up with the same theory, but he used matrices, so that's a little more difficult to look at. So if this doesn't seem like it makes much sense, it's because it doesn't really make a lot of physical sense. It just comes from purely math. So I'm going to go to another slide and look specifically at these quantum numbers and the rules for them. And again, the rules come out of what is possible mathematically. So we didn't make the rules, but the math limits certain values. So these quantum numbers, N, L, and M sub L are of course letters, but they represent the quantum numbers. So N represents the electron's energy level. Sometimes we call that a shell. And that corresponds to the distance that the electron is from the nucleus. N always starts with 1, and the values are positive integers. So that was the same N if we drew the hydrogen atom. The circles around the nucleus that we use to calculate the energy difference if an electron is excited to a higher energy level or falls to a lower energy level. So that N equals 1, closest to the nucleus, and then 2 and 3. That is the principal quantum number N. So that describes how far away an electron is from the nucleus, or its energy value. So the higher the N value, the higher the electron's energy is. L is the angular momentum quantum number, and L depends on N. So L depends on N. So it's a subset so to speak, of N. So we are going to call that a subshell. And some textbooks call this a sub-level because N may be referred to as an energy level. So the values for L always start at 0. So we have to make ourselves start counting at 0. And they go up through N minus 1. So when N equals 1, that means the electron is at the first energy level. The L value would be 0 and go up through 1 minus 1, but 1 minus 1 is 0. So when N equals 1, there's only one possible value for L, and that would be 0. When N equals 2, then that's the second shell around the nucleus. That's also the second row on the periodic table. So when N equals 2, the values for L always start at 0 and go up through 2 minus 1. So that N minus 1 means that we can only go up to the number 1. So when N equals 2, there are 2 possible values for L. Always start counting at 0 and do integer values. When N equals 3, L starts at 0, 1, and goes up to 3 minus 1, which is 2. So in an introductory chemistry course, we may have learned that when N equals 1, we only are allowed to use one letter, S. When N equals 2, we get to use an S and then a P. When N equals 3, then we get to use S, P, and D. So each level on the periodic table corresponds to an energy value, and then the number of subshells equals whatever that energy value is. When L equals 0, that means we've got the spherically shaped s orbital, and that was the plucking of the string I had on the earlier slide. So an s orbital is spherically shaped, and this, if we square the wave function, this is really the probability of finding an electron in this region. So if you have a textbook, it probably shows a whole bunch of dots, very dense, and then getting less and less dense as we go out. The p orbital, we draw it like this. The orbitals really do not have boundaries, but it's much easier to draw them as though they did have boundaries. So you may recall that there are always 3 orbitals within the p subshell. So this is just one of those p orbitals. So all of those rules, again, come out of this crazy math that describes waves. So I'm going to go back to this. So we're going to do some examples in a few minutes. M sub L represents each specific orbital. So that is the orientation of space, in space. And M sub L depends on L. So this depends on L. So the values for M sub L, if we think of the number line, having 0 in the middle, and then negative numbers here, -1, -2, 1, and 2. Whatever the value for L is, here when L is 0, our integer values go from negative L to positive L, but there's no such thing as negative or positive 0. So when L equals 0, the only possible value for M sub L is 0. When L equals 1, then we're going to go from -1 through 0 to +1. Whoops, did that backwards. -2, -1. So when L equals 1, we go from -1 through 0 to +1. When L equals 2, we go from -L to +L. So there are 5 values for M sub L. these are arbitrary. If we're describing, if we're describing where an electron is, N has a very specific value. L has to have a very specific value. But then the M sub L values, again, those are arbitrary. So what M sub L represents, the way I like to think of it, is this tells us how many orbitals there are within a subshell. So the number of values for L, M sub L tell us that. So there's only one value for M sub L, and that value is 0. So there's only one, that means there's only one orbital. So when L equals 0, we have, that means that there's an s orbital, and M sub L, one value, means there's only one orbital in the s subshell. When L equals 1, that means we've got a p orbital, so that's something that we just need to remember. If we already know this order, s, p, d, and f, we just have to remember to start with 0. So when L equals 1, that means we've got a p subshell, and then within that p subshell there are 3 possible values. So these are the 3 different p orbitals that we're going to find around the nucleus. So some textbooks show the p orbitals separate. So one goes in the z direction, well, maybe we'll call that the y direction. This is in the x direction, and then the z-axis would be coming straight out of the paper in the 3rd dimension. So we try to draw that prospectively. That lobe of the orbital is behind the paper. So that might be the p in the z direction. So the number of M sub L values is equal to the number of specific orbitals within a subshell. When L equals 2, the M sub L values go from -2 through +2. So since there are 5 values there, that corresponds to the 5 different d orbitals that there are. And then the electron spin is +0.5 or -0.5. The spin is a unique quantum property as well. So if a spin is +1, that means we go 360 degrees to get back to where we started. So if I have this pencil in this position, if I want the pencil to return to its original position, I've got to turn it 360 degrees to get there. So that's normal. Spin 1/2 is very strange. That means you've got to go 720 degrees to get back to the original position. So it's almost like you got to go around twice to be back in the original position. So again, that does not make physical sense, but that is partly, that's the mystery of quantum mechanics. I've got one more sheet that puts this in a little bit better of a pattern. So that is here. And if we look at the N values as though we were looking at the periodic table, the energy levels, N equals 1, N equals 2 would be further from the nucleus. This would be the second row of the periodic table. N equals 3 would be the third row of the periodic table, or the third circle around the nucleus. So I'm going to show some shapes for a few of the orbitals. So if I think of the columns as the L values, so when N equals 1, L is equal to 0. So we always start with 0. And then M sub L, I'm going to put across the bottom here. M sub L goes from -L to +L. So when L equals 0, m sub L also has to equal 0. So when we're on the first level of the periodic table, a 1s orbital could be described by these three quantum numbers. If we go down to the second row of the periodic table, we still, when n equals 2, we still have L equals 0, because we always start with 0. So that automatically means m sub L is still 0. So a 2s orbital is going to be larger in size. So a 2s orbital, or an electron in a 2s orbital, could be described by n equals 2, L equals 0, and m sub L equals 0. That would describe where that electron is. And when we're on the second row of the periodic table, when n equals 2, we get to have two values for L. So this next column, this would be representing when L equals 1. So remember from the previous chart, when L equals 1, that automatically means a p subshell. And I didn't write that over here. This means an S subshell, but we rarely say S subshell because the S subshell only has one orbital in it. So we generally just say the 1s orbital or 2s orbital instead of calling it a subshell. So here, all three of these orbitals are contained within the p subshell. So here's where m sub L is going to vary between negative L and positive L. So if we put negative 1 here and 0 and positive 1 here, and again, this is arbitrary, but so we could start with the positive 1 and the 0 and the negative 1. But this represents the three specific p orbitals. So if I try to draw them the same, so that the distance across here is the same as the diameter of that 2s orbital, that would be the p in the y direction. The p in the x direction would be the same size, but just have a different orientation in space. And then one coming out of the paper and going back into the paper. I'm not going to do this for every one of these. It's going to get a little bit messy, but you may recall that the p subshell always has three orbitals in it. So if we go back to n equals 3, then we're always going to start counting with L equals 0. So L is still 0 here, and m sub L is still 0. So one value for m sub L means one orbital within that subshell. So the 3s orbital is just going to be larger. When we get over to L equals 1, again, that's a p subshell. So those shapes are identical, but simply larger and higher in energy. So these are so the m sub L values would still be the same. Negative 1, 0, positive 1. And then a 4s orbital is just going to be larger. And I'm not going to, I'll do one of the 4 p's, I guess. Okay. So going back to the third level, when n equals 3, there are 3 quantum numbers for L that we can use. Start counting at 0 and 1, and here's where we add the L equals 2. And L equals 2 corresponds to a D subshell. And if you remember, the D subshell has 5 orbitals in it. And that the number of orbitals is the same as the number of magnetic quantum numbers. So since L equals 2, the m sub L values are going to vary in integers from negative 2 to positive 2. So integer just means a whole number, including zeros and negative numbers. So again, those would be our m sub L values. And the d orbitals are a lot of them look like clovers. So there's 4 lobes on most of them. So the 3 planes, the XY plane, the YZ plane, and the XZ plane, and then there's another orbital that makes a square along the XY plane, but points in a different direction, and the DZ squared looks like a p orbital with a donut around it. And these shapes again come from this very strange math. So a lot of mathematical equations give us straight lines or parabolas or circles and so forth. These equations give us these shapes of the orbitals. We'll use this type of a chart to write what's called an orbital diagram. So we pretend that we're going to put all of an atom's electrons in their lowest energy positions. So we'll come back and look at this without all of the mess of the shapes of the orbitals. The number of orbitals is always n squared. So I've got that written down here. For any given n value, there are n subshells and n squared orbitals. That's just the way the math works out. So when n equals 1, there's 1 subshell, and that's the s subshell, and there's 1 squared, which is 1 orbital. So that's why hydrogen and helium are stuck at the top of the periodic table, just 2 atoms there, because there's only 1 orbital. So hydrogen has 1 electron in that orbital, and helium has 2 electrons in that 1 orbital. You may remember 2 is the maximum number. When n equals 2, there are 2 subshells, S and P, and again, S corresponds to L equals 0, P corresponds to L equals 1. So we're just adding a few more quantum numbers to this from an introductory course. And then there are 2 squared, which is 4 orbitals. So if we go back up to this diagram, we can count the orbitals. Here's 1, 2, 3, 4. So when n equals 3, there's 1, 2, 3 L values, but we start counting at 0. And there are 3 squared, or 9 orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9.